have the password right. Okay. Well, good afternoon. My name is Andreas Kangelaris. I'm a professor in the Electrical and Computer Engineering department here at Illinois, and I also serve as a department head. And it gives me great pleasure to welcome you all here to this special event. This is a very special event celebrating a 60-year young man who is a very distinguished member of this department. He's one of those people that make this department what it is. There is a tremendous history in this department, and the continuation of that tremendous history is through people like Milton, who make sure that all the other people who are present here, all these younger faces that we see around us here, continue to add to this glorious history. So we are here to celebrate. And the best way to celebrate, of course, contributions, scholarly contributions, is by spending some time to think about what these contributions have done, what they're doing to the world, how they're changing our world, and why we are so appreciative for being part of those contributions through individuals like Milton. But before I start, I want to make sure that throughout the discussion today, if age comes up, we do not mention the word old. This is a word that I never came to terms with, especially in an academic environment, especially in a scholarly place, where all we care about is contributions and impact, right? And those things don't happen physically. They happen through the mind and through the soul. And so those things never grow older. They're always young. And somehow we sense it, we feel it, it's all around us, it's part of who we are. So that's why I said Milton is 60 years young, because that's the reality of it. And those of you who have the chance to talk with Milton and interact with him, you know very well that it's not only the mind that is young, it's also the body that is young, and the passion that is young. And these are things that have stayed along the way with Milton. And I hope you appreciate when I say that I don't have to say much about Milton's contributions to technology, his passion about making the fastest devices, his passion about continuing the dream of his teachers and his collaborators to make amazing things happen out of nowhere. I think all of those things we're going to hear a little bit through the presentations that come along. The only thing I would like to share with you is the following: that this event is special because I think it's special for the person we celebrate his birthday today. It's special because of the people who are present here to celebrate with him. I don't think there's anything more rewarding for a scholar, someone who has invested a big chunk of their time in an academic setting, doing research and teaching, than seeing actually the outcome of that effort, seeing the fruits of their effort present to share with them their satisfaction and excitement about that contribution. The students, the colleagues that are here, are going to contribute to what I believe is a very properly put together program that reflects of who Milton is and what he has done over the years. Now you might say, why 60? Why don't we do that when somebody is 70? Or I tell you, 60 is a very special number. For those of you who do not know, for a Greek, 60 is a very special number because if you think of the right-angled triangle, 3 times 4 times 5 is 60. And 3 square and 4 square add up to 5 square. So this is a very special triangle. The Pythagorean theorem is very important to Greeks, even though some people from India might argue that it belongs to them. But that's okay. But let me tell you, 60 is a very special number. As you know, we use 60 to describe many symmetries in nature, right? We use 60 to count time. Everything that has to do with symmetry, with a circle, think about how you define, think about a hexagon, or think about an equilateral triangle, or think about silicon, right? The crystal. Anyway, 60 is a very special number, and I think that's why the decision was made by people who have studied semiconductor electronics to say it will be during the 60th birthday that we're going to do that. Another thing that 60 brings to mind is the fact that Milton actually, I think it was about almost 30 years ago, maybe 31 years ago, that he finished his PhD. So you see, you take his age, you divide it by 2, you say, okay, the career before a PhD and the career after. And so the career after, the 30 years that followed his graduation from this department, were training in industry. He spent a few years to prove to himself that the industrial setting provides you with significant motivation to go to the next level, to innovate more, because industry sometimes tends to be short-sighted, not far-sighted. And so he came back and he made sure that he will continue, industry will continue to thrive in the years ahead, thanks to contributions that come from him. So with that, let me say that it is our pleasure here at the University of Illinois in the Electrical and Computer Engineering Department, in the Micro and Nanotechnology Laboratory, that we are holding this event to welcome friends, colleagues, alumni that are part of this special celebration today. Over the next few hours, we're going to hear some of the research that is related to the things that Milton has been working on, is interested in, keep him awake at night, keep him smiling all day long. These are the things we're going to hear about over the next few hours. In addition to that, after some formal presentations, we're going to have the opportunity for everyone to come up here and, without any hesitation, sinus, or anything else, share with us some of the things that have been doing since they graduated from here, some of the things they remember from the days they were working with Milton. Everything that you feel makes your presence here a part of this celebration. So with that, I would like to start by welcoming the first speaker in our presentation, someone who needs no introduction, Professor Nick Holoniak. As you know, Milton is the Nick Holoniak Junior Chair in the Electrical and Computer Engineering Department. And frankly, I cannot think of any other award or recognition that Milton has received that is more meaningful than holding that chair. So Professor Holoniak is going to share with us some of the most exciting things that I think are happening in semiconductor electronics today, how a transistor is changing into a laser. Nick?
Thank you. Thank you, Anthony. Hello, everybody. Good afternoon. I'm sorry it's so hot, but I prepared for it. I was wondering what this thing was. I thought it was some kind of a Greek.
It's not
some sort of a Greek spying device or something, you know. Anyhow, there's always miscommunications, and I didn't realize your little brochure was going to be basically abstracts. So I prepared the front end of a paper, and I assured Milton that we're going to go back in there and extract some of this for other purposes. But I pointed this at him specifically because even though he's not as old as the transistor, he's almost as old as the transistor. The transistor is actually goes back to Bardeen and Bratton in 1947. So you figure it out. A couple more years, it's 65, so it's past 60. So Milton, he's still a young man relative to the transistor. But the transistor is pretty damn young in terms of many things it can do. And we've had a lot of trouble trying to make people understand what this is. What are we doing? So I thought, okay, I'm going to go right back to the beginning. All of you who mess around with semiconductors think you understand devices and all that. If you don't understand a point contact transistor, you better go back to school, because that's where it all begins, and it does not begin with Shockley. It begins with Bardeen and Bratton. And I wrote a little bit of the piece of this in there. I'll read you some of it, but I'm going to skip in places because you can read it for yourself. I start out saying, arguably the most important transistor ever was the Bardeen and Bratton point contact transistor, December 1947. It's the original bipolar device, the original bipolar triode device, where you use plus and minus. See, up to that point, and I go back to that point, we're just using electron. We're just bumping electrons along in copper. We're just moving electrons in vacuum tubes and all that. We're not using plus and minus charge. And if you're dealing with a gas, you're not dealing with the same thing because the ions are not locked in place. In a semiconductor, all the atoms are staying put, but you're moving plus and minus charge. So, something different is happening there. And it's Bardeen and Brattain that come up with the device that indicate that it isn't just the negative charge that matters. The crystal is N-type, but positive charge is involved. That's Bardeen and Brattain. That's not Shockley. Shockley gets a piece of it later. At any rate, this is the device that's the prototype. It's the device that doomed the vacuum tube, changed electronics, led to the IC. I can tell you more about that. Led to a vast new electronics, made possible a large-scale computer. While people here, when I'm a student, they're running around talking about Turing machines and all that, they don't know they're not going to make a computer with vacuum tubes. In fact, the first ILIAC was vacuum tubes. It's the transistor that's going to let them make the computer. And Gates didn't do anything. Take away the transistor, he's nobody. It made possible a large-scale computer, led to the diode, laser, and LED. You wonder why? Because if I got electrons and holes, they annihilate one another, and that's the basis to generate light. You either generate heat or you generate light. Now that we got that kind of a thing, we're going to study recombination and find out what this kind of light is. So you can make a direct connection from the transistor to the whole business of an LED. And if you see it taken off now, what you're seeing is how many years it takes to get things done. That's why not even Milton's going to be around to see what the transistor laser is going to do, because it's going to go now decades, 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 decades. And unless Kurzweil is right, you're not going to live from 100 to 200 to 300 to 400. And he's not right. In a time of little or no semiconductor device understanding or technology, the point contact transistor, a revolutionary new bipolar plus-minus triode, employing the hole on an equal basis with the electron, is the device, in fact, the device that taught us about the importance of the hole. What the hell is a hole? When we first heard that and saw that, we thought these guys were crazy. In fact, there was a professor here who was considered a big-time professor, and he laughed at it. He said, that's just a construct of the physicist. That man was totally wrong. You don't even hear about him anymore. There was no technology, but what they did was ingenious, because with no technology, with a primitive crystal, they make a triode that's totally revolutionary. It was just the required amount of what they needed. It was a base. What I'm pointing at is the base that is everything. It's the base. Just a small crude slab of germanium, the base crystal with an ordinary ohmic contact on it, and then a point contact emitter, low impedance, and a point contact collector at high impedance, and that was everything, because it's the base that's separating emitter and collector. And if you cheat a little bit and suck up a little bit of that emitter current as recombination current, as base current, you can separate emitter and collector. So you can separate low impedance front end from the high impedance output end, and that's the basis for gain. All you have to do is play around with Kirchhoff's laws and add up the current equations, and you'll figure that out right away. And of course, that's the basis of the name. Low impedance input, high impedance output, a transfer resistor or transistor. And also there's some Bell Labs politics that gets involved in that, because you can't call it a tron, because that would be GE or Westinghouse or someone like that, but it can be varistor, resistor, thermistor, and it can be a transistor, okay? So anyhow, it was not anyone's previous idea. Field effect was a known idea. Shockley wanted everything tied up with field effect notions in some of his stuff. It wasn't a field effect device. It was a different device. For what it was and what it revealed as just progenitor alone, it outranks all of the transistors. Writer like Gilder saying that the point contact transistor set back the transistor is an idiot, because there is no transistor before the point contact transistor. It revealed the idea. Everything else and the work of everyone else came later. All of you who've ever touched a semiconductor. All of your work comes later. And you know what? It's not obsolete. Because if you go back and understand that, you understand to focus on the base and what the base does. And now we start to run in and collide with the present. And what people have done to the transistor and pushed on it and leaned on it and so forth. And we start aiming at people like Milton and the HBT, because when you get to the business of the HBT, what you're doing is concentrating inevitably on the base. The man was driving me crazy with what he's telling me about his numbers. Not about his device, but his numbers, because he's dealing in some fantastic numbers. He's telling me about high current densities. And I know about stuff like that because I've been in that area, and power devices and all that. And he's telling me about high gains, but I know there's still a lot left then that's base current. So there's got to be something that we can look at in the base current. And he and I both begin to zigzag back and forth and talk about this and try to figure this out. And what can we do with that base current? Because it's essential. It's part of the transistor. Could it in fact yield a laser? We came to the conclusion it's got to be a light generator. And at first it's hard to see, but then Milton and his guys figure out how to do this, and we see it. So it's focusing on the base, which is an idea that comes right from the point contact transistor, and you can ask why the point contact transistor? Because it's only the base that's semiconductor. And there is no transistor without the semiconductor. So it's pointing to you, and yeah, thanks, Milton. And so you see that it's teaching you a lesson. It's teaching you where to put your mind. And that's right where he has his mind, because if you look at what he's doing, he's shrinking the base and jacking up the doping and shrinking it, and then he's shrinking the dimensions and shrinking the dimensions. And we're not, incidentally, we're not really learning a lesson from nano this and nano that and nano everything. We're not learning that lesson from all that hype. Because, in fact, semiconductor people have been going that way all the time and have already put quantum wells into devices beginning in 1977. And so we're just using angstroms, which is 10 times smaller than a nano, and we're not talking about an angstrom world, angstrom world, angstrom world. I don't know, maybe that makes Cangelaris unhappy, because nano is probably a Greek word and angstrom is a Swedish word or something like that, you know, but that's propaganda. Anyhow, so you examine all of that and look at what you're being taught by what these devices are, and you come to the conclusion that the energy gap is fundamental, and the separation from input to output is fundamental. The input and output separation is the basis to have divide current from input to output and have that third current, which is so vital. And the energy gap is fundamental because it's the connection between electron and hole. So the semiconductor is everything, and the transistor is everything for what it's teaching. And the base current is everything because it's saying, are you going to throw that away or are you going to use it? And so we came to the conclusion that it generates light and that we can use it, and that the base is inevitably a cavity of sorts because it's layered. And Milton and his fellows are putting geometry on the edges and changing it and all that. So it has a certain small volume. And that small volume, if you take the wavelength that's involved, tie that to the energy gap, and take that wavelength and divide by 3 or something like that, and you need a half a wavelength or so for cavity reasons, and you find out that all the things are agreeing. The energy gap isn't pushing you this way, and small size for speed isn't pushing you this way. The two are coming together. And what he's doing is exactly going in the right direction to make higher speed. See, the world has learned how to make small stuff and integrated small stuff. Incidentally, I don't know how you're going to do that with carbon nanotubes, because you have no science of assembly of small particles, not alone a good device to assemble. But the semiconductor people have learned how to make smaller and connected, because the crystal is connected to begin with atom, 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 and now it can be layered and put geometry in it and structure in it and doping changes in it and other changes, edge changes, and geometry in general. And to make integrated circuitry, you have to be able to make some kind of an integrated geometry. So you want something connected on which you can impose some more geometry of form. And you can see what was the magic about the semiconductor and the transistor and where it's all pointed in the end. At any rate, so the question then comes up, can you make this device that's generating spontaneous recombination, can you make it generate stimulated emission? And his transistors are in the right form for us to make modest changes, because we know that we can manipulate the recombination. We know we can put quantum wells in there, call them nano wells if you wish. And we know that, and we know that we can change the recombination, and we can bring the gain from around 100, where he's got a beta of 100, that is the ratio of collector current to base current. And if he goes to lesser gain and turns more of it into recombination, he gets more gain, he gets more bandwidth. He doesn't get more gain bandwidth, but he gets more bandwidth, so he might want, for transistor reasons, to actually have lesser gain. And we want it for recombination reasons, and so we go ahead and do that. And at any rate, you have then simultaneously a device which is a transistor, and if it goes into stimulated recombination because of what the base current is doing and driving a little cavity, you have a laser. You have both. You haven't lost base control in the fact that the base is doing what it does and it's three-terminal, and you haven't lost the fact that the base charge is tilted and pinned and not like in a diode floating up and down. In fact, I consider professors who can't see the difference as dumbbells. How did they get their PhDs? I mean, I can't understand that, because when Milton is describing this to the world, they're picking on him and saying, you don't know anything about lasers. And they don't know anything about transistors and recombination and semiconductors, I don't think. At any rate, it was obvious to us that when we got to that stage that when you turn this device on and it goes into stimulated emission, the recombination rate is faster. That means the transport from the input to the output has been reduced. It hasn't been taken away, it's been reduced. So in all the textbooks that show you collector characteristics, and you've all studied transistors and you see these nice uniform characteristics, and my guys that are good with computers counted the books, and a couple thousand books, none of them ever showed what's going to happen. But now the transistor laser, when it becomes a laser, the gain compresses, the characteristics go up normally, but then they hit stimulated emission, the lifetime goes down in the recombination process because of the stimulated emission, and the characteristics compress. Holy mackerel. That's fundamental. A transistor's never done that. It has now, and that means something has happened to the transistor, and transistor people had better think about it, because that means you can redesign transistors. And that also means that you have another signal. And it's a signal in the optical domain that is not in conflict with what you're doing in the electrical domain and speed and all that. So from the standpoint of things like Maxwell's equations and Kirchhoff's laws and all that kind of stuff, the DC bias is current and electromagnetic field and all that. So is the microwave arrangement that you've made into the device and its contacts and stuff like that. And also the signal that's being generated optically, which is the base current. That's not throwaway. In fact, before you're done, you better take another look at Kirchhoff's law, because you can take that signal out, feed a detector and put currents back in there and be writing different kinds of current conservation equations. And that's been part of all this too. But I'll let you read some of this for yourself. I've obviously deviated from the text, but there's a few things that have to be said. I better look to see what they are. Normally I use slides, and I use the slides to guide me. And this time I didn't do that. Okay, Now, there are other issues that pop up. This optical signal that you have from in the inside of your device is not an optical signal that you're getting like using the device as a detector and getting this signal from elsewhere. So that signal, the device doesn't care where it's getting its optical signal. It could get it from the inside or get it from the outside. So you find that if you transport an electron from, let's say, the emitter into the base, and you've put a quantum well in there, and the electron recombines with a hole, that means that the hole came from somewhere. It either came from the base contact or an electron tunneled across, aided by the photon you just made and absorbed, and aids by the Franz-Keldysh effect in tunneling. So you can start looking for tunneling effects, which are internal tunneling effects. You can look for tunneling effects that you can build in. In fact, if you build your collector as a tunnel collector, you can make a fantastic nonlinear device to mix microwave signals, and that works. You can get negative resistance effects due to the internal tunneling of the Franz-Keldysh effect. You get all kinds of interesting stuff like this, so you're restudying your transistor. Then you look at this and you say, wait a minute. This is a device that in places like Zindium, which I think Milton knows about, they integrated some of this stuff. In fact, Shen here and some of the other people know about that, and they know that you can integrate these things. So these three terminal devices of his HBTs integrate. But integrating, he tells me, when you deal with Intel and people like that, when they go from device to device and they want to raise the speed, the clock speed higher and higher and higher, the propagation speeds, you have to deal with transmission line effects and all of that, and loss effects and so forth. But if you talk to Fred Kish, he says, but you know something? We put lasers into integrated structures of various kinds, and we send signals for thousands of miles. Well, there's a different kind of process going on. Those are dielectric index change reflectors, and that's not the same thing as reflectors with metals where the field is driving charge and then a resistive action is heating the thing and all that. In other words, there's another way of passing signals around from device to device, and that's optically. Well, that gets a little bit scary now, because if we can manipulate these things and make good cavities and low thresholds and all that, this means that you're going to be generating integration possibilities up on top with how you've built this stuff and done ordinary IC work, but you're going to also integrate internally with how you pass an optical signal around that's coherent. Now, that's all in the cards, and incidentally, I heard enough for various reasons that I'm not the guy that's going to do that. You are going to do that. You younger people are going to do all of that. Because if an older person, a professor and all that tells you, we did it all, they're lying. There's always much more to do. And look, I would love if John Bardeen were alive and Greg Stillman, because they'd see right away what we're up to, and Stillman would be right in the middle of it with us. And John would know right away how this ties together to the point contact transistor and all that. In other words, the older people don't get very much done. They get a little bit done. And you always need the younger people to come in and learn more and further and add to it. Now, I've skipped around a lot. I'm a little bit more orderly in what I wrote. But I thought, that'll get boring if I just read it to you. So I won't do that. But I do want to mention a couple of things. One of them is the point contact emerged basically from something that Bardeen had figured out about surface states. And then he and Walter Bratton did some more stuff trying to build a field effect device, and they got a crude one. And then in some more fooling around, we could go into that, but I don't want to do that. There's time limitation. They come up with the point contact transistor, which is totally revolutionary, no one's idea. And that's the beginning of it all. Now, Milton Fing is building HBTs and squeezing them and pushing them, squeezing and pushing them. He's doing something that all of you who are physics inclined and so forth ought to understand. If you don't get good data at room temperature, sure as hell, go down to low temperature. Go down to some other extreme. Either push higher, push smaller, something. In other words, don't sit there spinning your wheels. Change something. Do something. And so what he's doing is he sees that the HBT's got a lot further to go, and he sees he can do it. And he's not thwarted by bad decisions of other people. He's making his own. And he's squeezing and squeezing, and he's squeezing the thing to extreme limits and performance. High current densities, some special things that are not burning his devices up. There's got to be reasons. And that will, when you turn to find the reasons, you find, there's photons. When you begin to get photons, you begin to ask the question, can I make it stimulated? So you're going this way, but then suddenly you see something that causes you to go that way. Bardeen and Bratton are going one way and going in this direction, but then they see something that causes them to go this way, and something else happens. In other words, you cannot plan exactly. When you're dealing with a venture capitalist, he's an idiot if he thinks you can turn it into money right now. A few bucks that he's putting in and can be turned into money immediately. You may have to turn a lot of directions and do a lot of fooling around and take some risk. One of our guys has been into this, and he told me some years ago, he's sitting here, that you do 10 of these and you're lucky if you get 2 or 3 that work, because you can't figure that all out in the beginning. You're going to make some blunders and mistakes, and you're going to have to learn along the way. Okay, so what I'm saying is, the transistor laser, a high gain semiconductor medium. All of the laser people have come to the conclusion, if they're going to make a tiny laser, it's going to be a semiconductor. Then they go and do all the wrong things, and to make it small. They can make it small, but they make it a dumb way. It's a high gain medium. It's a solid density of atoms. It's not chromium and ruby or a few gas atoms here and there and all of that. It's high density system, and that means it's high gain. The smallest system I know of like this is about a micron thick and about a micron in diameter. In other words, I know it can be extremely small. I don't know how small it'll be as a transistor laser, but it's going to be small. It's a high gain semiconductor medium admitting to ultra small electrical and optical size compression. That's a big advantage. It well may become a combination ultimate transistor, ultimate laser. I can tell you for a fact that a p-n junction is an ultimate lamp, and it's the basis for an LED. You can prove that from first principles. I'm suggesting the word use of the word ultimate because you can see the basis for an ultimate combination transistor laser, because it has all the 3-terminal power, and it also has this other issue. An ultimate transistor laser. It is unique as a transistor and as a laser. It is both. It is not 2 p-n junctions in forward bias feeding a common base. The Japanese have tried to climb on board, throwing that kind of specious thing at us, some sort of stupid thing. It's not that. It is not an exaggeration to say that the transistor laser, so surprising and offering so much, is the most important thing that has happened to the transistor since the transistor. It was not possible before Milton and his HBT. It wasn't possible. But I'm suggesting to you, you can say the guy is old, he's dumber than hell, he's losing it, and he doesn't know what he's saying. But I maintain that the transistor laser is the most important thing that's happened to the transistor since the transistor. It's sort of cannibalistic. It's in my opinion, I haven't seen anything like this in decades around here. And it is now 55 years since Frosch at Bell Labs in 1955 put the oxide on silicon. You know why I know about it? Some of my crystals were the first ones that had the oxide on it. I was working for John Mull, and down the hall is Frosch doing some of our diffusions, and I know which of my crystals he burned up and which ones had the oxide. And then later, and some years later, I'm recovering from one of these goddamn surgeries, and they still get me to go to Washington to testify. And I didn't feel I owed it to Bell Labs, but I feel I owed it to Frosch, a wonderful man. In fact, the integrated circuit really belongs to him and John Mull, who saw the basis for it all, and Frosch and the oxide. and noise forbidding the rest of us to metallizing across from device to device. And see, now with the transistor laser, we'll not only metallize across and across from device to device, but we'll waveguide also and do some more. At any rate, that's 55 years. It'll be interesting to see in 50 more years what speed and kind of integrated circuits will come from the transistor laser. The HBT has become much more than a high-speed transistor. And I point at Milton Feng as being the man who's at the basis of that. I want to mention that I was John Bardine's first student. All I did was harassed him, bothered him, argued with him, but we did this together, and I didn't sit there smarter than him than he is, and he's smarter than I am. We were bashing on one another friendly, not tearing one another up, but saying, "Ah, you're full of baloney," and no, it'll work, and we go ahead and do it. I want to mention that I was John Bardine's first student. Greg Stillman was one of my first students. How many of you were Greg Stillman's students? Okay, yeah, there's Dave over there, Omari, and some, you know who I'm talking about. And Milton Feng was his first student. Also, Milton was a guy that I taught in class, and then later other things happened and other things happened. So we've known one another for 35 years. And we're used to one another. If John were still here, I mean Bardine, I am sure he, as would Greg Stillman, have a big smile seeing what has happened to the transistor. And it is still in our blood. Still alive and well, and still revolutionary, thanks to Milton Feng's relentless pursuit of the HBT. You have to be tough. You have to be smart, and you have to be tough. And Milton was both. And he was not going to let go of it. It was like a bulldog that had meat in his mouth. He's not going to turn loose of it. And pushing it into extreme operation, to tiny size, to high current density, to high speed, and into the realm of many fundamental questions and new insights. You learn something. And as a consequence, many new opportunities. And I'm at the end. According to a well-known sage, Fred, where the hell is Fred? Fred, I know you're a Yankees fan. Well, I'm not a Yankees fan and all that, but I am a fan of the next guy. According to this well-known sage, it's not over till it's over. Now, including the transistor and its laser operation. You know who I'm quoting?
Yogi Berra.
Yeah, Yogi Berra. Okay, all right. Now, I don't know if I've left any time, but you're welcome to attack me and tell me I'm wrong. So, want me to fill in something?
Thank you very much.
Thank you. My back is hurting me. My back is hurting.
So, do you have any time for harassment? Is that what you call it, Nick?
I don't
Asking
care.
people questions, you call it harassment?
I'm talking to some Russian students in Leningrad, Polbar, and I asked them at some point, I said, I'm an American, I'll answer any question you got. and one of the kids finally says to me, what's your move? Why? He says, you speak Russian with a Ukrainian accent. I thought that was funny. He didn't accuse me of having an American accent. For all of you who speak other languages, don't worry about it.
And I just want to mention one thing, right? For the past couple of years, no one can invite Nick to give a talk, So it's very refreshed for all of you guys to have opportunity to get a lecture from him today. We've been hiding that lecture for the past couple of months. I didn't even know what he was working on. Even until 12:30 today, I was very short.
Well, just because Nick brought it up, I can't help but tell you that I was back home trying to give a seminar, back in Greece, trying to give a seminar, and I tried to give a seminar in Greek. So the truth is that I've been in the United States for a long time, 30 years.
Did it work?